Yes, today I am going to speak about the future of broadcast television. My name is Pablo Angueira. And because of speaking of broadcast television, terrestrial television, who comes first? Commercials. So first, commercials. Broadcast Technology Society. The Broadcast Technology Society is one of the societies of the IEEE. The IEEE is divided into 50-something societies. This is one of them. This is the oldest society in IEEE. We were founders of the IEEE. It's a membership organization who is open to everyone that want to participate. The mission is to serve the needs of the members, of the participants, and mostly is to enhance professional knowledge, keep them informed, providing educational programs like this or other scientific networking opportunities. Benefits for members, you can stay current with developments in the industry. You will have access to IEEE publications through IEEE Explore. There's BTS TV, there are chapters worldwide, and I will take the opportunity to encourage you. Dr. Dmitry Tachenko, he's the chair of the chapter society, joint chapter, the society chapter of Consumer Electronics Society and BTS Society. It's a joint chapter hosted by two societies. So if you are interested in broadcasting or in consumer electronics, here you have two opportunities to approach Professor Dimitri and then become part of the chapter, who is just for your interest. And then you have other potential benefits like discounts on conferences, on industrial events, meetings, and a lot of networking opportunities for your future career. One of the programs of the society is the Young Professional program. This program is focused on people, on you, that those of you who have finished your graduate before 10 years. I mean, you are not older than 10 years after your graduation. This program was called in the past Graduates of the Last Decade, the Gold program. So I'm not any longer a Gold member. So this program, the main objective is to provide an opportunity to very young professionals to have connections with those who are not any longer so young, but have maybe a good opportunity to help you come into the industry, maybe give advice. Maybe you can learn, I guess that most of you are engineers. This is an opportunity to learn and to attend education initiatives which are not technical, but really useful for your professional career in the industry. And you can find more information on IEEE initiatives in these videos that you can check. So this talk is sponsored by the Distinguished Lecturer Program of the BTS Society, and this program provides a means to chapters. I was invited here by the chapter here in St. Petersburg with a lecture on a topic which could be interesting for the chapter, on topics hosted by the BTS Society. So you already know my name. I am Pablo Angueira. I am a professor at the University of the Basque Country. I am associate editor of the IEEE Transactions from Broadcasting, and also I am the current IEEE BTS Publications chair. And my background, I belong to one research group at the University of the Basque Country. We are a group of 20 people. Half of them we are staff, and the other half is contracts and postdocs and researchers, and we work on physical layer of wireless systems, mostly associated with broadcasting, but not only. We are very active in physical layer system design. We participate in creation of standards. We have done a lot of RF tests, monitoring and measurement, also linked with a network planning. We did in the past when I was a PhD, lots of field measurements, field tests with the first DTV networks in Europe. And lately, we are working on a big data analysis to improve planning of networks. So big data associated to network planning. So if any of you are interested in cooperating with our group, just send us an email. We have always open positions for smart PhD students. So if any of you want to stay 3 years in Spain, in Bilbao, doing your PhD, we have positions available. So the audience, I don't expect you to be experts on broadcasting, so you will find that some parts of my presentation might be very basic for you. For you who are very experienced in the broadcast business, maybe they are very simple topics, but unfortunately broadcasting has been eliminated for university programs worldwide, and sometimes I have to explain very basic things that in the past were basic for graduates. So it is a tutorial-like talk, and the topic is future of broadcast television. I will give an outline, and I will show it now. I will talk about audiences, some statistics of the broadcast industry. I will talk about content and the implications of content. I will give a brief description of the two latest DTV standards, is Dvb-T Two and ATSC 3.0, the standard in the US and Korea. I will talk about a very important issue in the next years, which is spectrum, the use of the UHF band around the world in connection with 5G, and I will talk about some future directions. So first of all, I'm talking about video content. You will be probably familiar, many of you, to this type of statistics. Every year or every 2 years, Ericsson, Cisco, and all these big companies, they release some statistics about the type of data which is carried by their networks. And they all agree more or less that by 2020, 3/4 of the traffic will be video. And current networks are not prepared to handle this increase in video content traffic. But video is many things. Video is broadcasting, which lately this is being called audiovisual media, not only broadcasting. Audiovisual media is also social video, which is very big today. It is music and video on demand. It is video for e-learning, very big now in Europe. It is security, it's medicine, it's industry 4.0, another very big priority now in Europe. It is gaming, a lot of things. There's a commonality between all these services, which is the huge bit rates required to deliver these services. And there are different factors that differentiate between all these different services, which is the number of users and how you manage the user access to those contents is different depending on the market. There are some services that require roaming, and also, very important, the understanding of quality is very different depending on which service we are talking about. This is key for then system design. I am talking about audiovisual media services, and these are some of the features that audiovisual services have. First of all, the purpose of audiovisual media is to provide programs to the general public. The function is to inform, to entertain, or to educate. There are some obligations associated to the content provider, which is not the case in many other video-related applications. So the producer of the content is regulated somehow. And these services include what we understand as traditional linear TV, live TV, but also on-demand TV, time-shifted, non-real-time, interactive TV, multi-screen, multi-services, and other platforms. So with this scheme, we can have an idea of the delivery chain. You have the services on the left. Let's say the most traditional one is the linear services. And you have two options to deliver the services. You have broadcast networks and you have broadband networks. Broadcast, we have the satellite platform, the cable platform, and the terrestrial platform. And I have included, these are the three traditional platforms for television. And I have included here a fourth platform, which I consider it also broadcast, which is eMBMS, or future versions of eMBMS. What is eMBMS? It is the part of the LTE standard and future 5G, who is just not identical, but very similar in concept to digital terrestrial television. It is one B node delivering a downlink for a group of users inside the cell. So it is another terrestrial component. But in this case, and I represented that with that chain, it is linked to the unicast services. It is linked to the unicast network. And this is a very important implication, because here is a discussion if someone without a SIM card, you are not subscriber of the cellular operator, are you going to be able to access these broadcast services? Will these services also public television? Will there be commercials, advertisement on that eMBMS service? So there's not a clear idea yet in the market to answer these questions. And then you have the fixed broadband with the OTT services like Netflix and HBO and all those subscribing companies for OTT. I will not go one by one, but here is a summary of the advantages and disadvantages of the traditional broadcast networks and the IP cellular networks. You can summarize them into broadcast is very good and very efficient in the downlink. It's very efficient because it serves a lot of consumers very efficiently in price. The cost, very efficiently in cost, I mean. The cost is not proportional to the number of viewers. It is constant. The drawback or the weakness of the broadcast is it is just downlink. So any type of feedback or interactivity is really limited, right? You turn it down, you turn it up, and then you have the broadcast platforms, which is the beauty of those platforms, is that these are very good for interactivity. You always have a connection with your consumer. But, which is the bad part, it is limited coverage. They have a limit, and the network currently easily saturates with the number of consumers. So you have very good interactivity, but the cost of your delivery is proportional to the number of users. So next year, here, it is this year. Look, I'm not a fan of football, so forgive me for that. It is this year, the championship here in Russia, or next year, it's this year. So if the day of the final, everyone is watching the final on the cellular phone, the network collapses. The network is not able to cope with these big audiences. So some numbers on audiences. Look, these are statistics taken from that operator, Statista. From 2009 to 2016, the other ones are projections or estimates. And you see the number of minutes that we dedicate, this is worldwide. Number of minutes we dedicate to watch television, and the number of minutes we dedicate to be on the internet. And you see that television is declining, not much, more or less stable, but slowly declining. And you see the increase in the internet. Now they should be more or less equal. And this, I will show you now, is very different depending on the age. Those of us who are older, we dedicate maybe more time to stay on the TV than on the internet, but young people, and these are, well, also these are statistics in the US, which is a specific market. But you see that nowadays, smartphones already beat TV in the youngest sections of the population. Also, and this is another interesting statistic, in Europe, North America, and Middle East and Africa, we still watch television on the TV. We just, when we want to see broadcast content, we choose the television set. But look at Asia. In Asia, already people watch television more on the cellular phone or similar device than on television. So the question, and I do not have an answer, is in the future, are we going to be, okay, thank you, thank you. In the future, we might go to that environment, to that situation. Here you have the detail for some European countries. I did not include all of them. Here is the average of the European Union. Still very similar numbers as I mentioned before. Internet viewing is not so high. And now, specifically to terrestrial in Europe, these are EVU data from EVU statistics. 88% of the population in Europe is reached by terrestrial television. And the average, and this is something that still amazes me, the average of Europeans watching television is almost 4 hours. 3 hours and 40 minutes. How? I mean, we do not work. We do not sleep. 4 hours. And this is average, so it means that many people watch television more time than every day. Every day. And also very positive for broadcasters, but still it amazes me even more. You have 24 years, you're 24 years old, and you spend 2 hours every day in front of the television. And then you have to cut the recording. Find something interesting in your life. Don't spend 2 hours every day on television. So now seriously, the trend in Europe. More or less, this viewing average is stable since 2011. Well, there are variations from year to year, but they are not relevant. And again, there's a show here that for young people, I don't remember the range of ages that EBU was considering. I think that they did not give the numbers. But you see a slight decline from 5 years ago. So the future maybe is more similar to that graph on the right. Linear TV. The traditional share between the share between traditional linear TV, direct, and non-real-time television, you see that in that graph is increasing, but not much. Really, it is about 15%. The share of the non-linear TV, the on-demand TV, with respect to the linear one, and these are data from Digitag in 2014. Now, country by country, here you have, colors do not appear here very well. You have countries with heaviest viewing, which are this area, also Russia, Portugal, also Turkey. They have heaviest viewing. Countries in the north of Northern Europe, they have the lightest viewing rates. And then in the middle of Europe, we have moderate viewing time. If we look at the platform, 40% more or less is terrestrial. These are numbers for the whole Europe. We have 28% for cable. Satellite is around 23%. And broadband, this is IPTV services, is around 10%. But this is the one who is increasing faster nowadays. And these are data from BNA. If we look at the countries, here we see a very big difference. Countries in the south of Europe with UK is what we call the terrestrial countries. In the middle of Europe, these are countries for cable TV, mostly cable TV, a little bit satellite, but mostly on cable TV. And the rest of countries here in the north of Europe, I didn't have the statistics in this map for Russia, but countries in the north of Europe are a mix between cable, satellite, and terrestrial television. If you look at the graphs, and these are numbers from this year, this is the penetration of the terrestrial platform in Europe. So you have here again similar numbers now with exact percentages. You have Spain, Greece, Italy, Russia also is a big terrestrial country, United Kingdom, etc. This means penetration, the share of your market, and it's always estimated on surveys because free-to-air television, terrestrial television, does not pay a subscription. So it's very difficult to estimate if you watch television at home by terrestrial or not, even if you have other ways of getting television. And then you have countries in the middle of Europe, here, Netherlands, Austria, Germany, Belgium. They are more cable countries and satellite countries. These data are taken from the DVB database, which is updated every 2 months or 3 months. And now, other platforms. If you look at country by country, the situation in each country is very, very different. From countries where satellite is very big, like for example, United Kingdom, or countries where cable is very big, for example, in Sweden, you cannot define a common model for every country. And this is one of the problems of the broadcast market in Europe. If you look at the number of programs delivered by terrestrial television, look at these numbers. Whenever you find a 0, means that I didn't find the data associated to that value, right? So now, because I was talking to Dimitri, I know that in Russia, all of them, they are public. You have 20 programs, and all of them, they are public. The share in other countries, for example, Spain is here, yes. We have five of these 26, they are public. The rest are commercial television. And in some countries, and Italy, for example, and in Spain, for example, local TV and regional TV is one of the very big aspects of digital terrestrial television. And this is where some operators are trying to look the niche for the business. Why? Because cable, satellite, and IP do not match so well this business of local TV. For example, ST-PETERSBURG TV, or some cities in Spain even have more than one program for local television. So summarizing the statistics on audiences, terrestrial is the fastest growing broadcast platform yet. If you look at the whole picture of the planet, there are more than 200 million of receivers already sold on the market. In Europe, the coverage, which is not the market share, but the coverage is almost universal all across Europe. The program offer is really high, and especially, again, this is applicable to Europe because you have a lot of languages, a lot of cultures, a lot of specific programs for many regions. More or less, you have half of the programs are public and half of the programs are commercial TV. The exact numbers were 50-something versus 40-something, but more or less half public, half private in Europe. And HD TV is already available in most countries in Europe. So viewing time of linear is about 3.5 hours per day, and still terrestrial television is the most popular single platform for audiovisual content. So these were audiences. Now we are going to speak a little bit about content. Look, this is the delivery model chain that EBU proposes to describe the broadcasting model. You have here content. This is the creation of content. This is aggregation into one platform. Excuse me. This is the delivery method. It could be terrestrial or cable, satellite. So they call it distribution. And this is the reception. And now with content, I am going to try to explain or to highlight the relevance of what we do here, especially in terms of formats, on what we have here. The implications on the capacity of the standards, the efficiency of the standards in order to deliver this content. So contents, formats. We have from a standard definition, this is the old resolution in Europe for vertical resolution, comes from analog TV, up to the ultra high definition 4K. So currently in many countries, including my country, we have still most of the programs are standard definition programs. I think that here in Russia also, even with Dvb-T Two. And this table contains the average numbers for bit rates for compression output that you require per program. And the table contains MPEG-2 and MPEG-4 versions. So nowadays, using a statistical multiplexing, we can deliver one program more or less. This was a little bit pessimistic, and this is data. These are data from 2016. So let's say 2 megabits per second. They are enough today to provide a standard definition program with a quality which is quite acceptable. And you can find all the tests to get these numbers in this EBU document. So this is standard definition. If we go to high definition, and now high definition, I'm talking about 1080p, which is almost 2,000 pixels horizontally, 1,000 vertically. And these are numbers for HEVC. So it means H.265, which is the next generation of coding, the one that it is being used in the latest equipment today. You have 3.6, 3.8 megabits per second. If we would use MPEG-4, this goes up to 6 megabits per second. But these are the numbers that we used for standard definition, maybe not 10 years ago, but 7 years ago. So today, with high efficiency video coding, so the next after MPEG-4, so H.265, we can deliver the same compression, or the same bit rate, sorry, for an HD program. But is this enough? And the answer is no. Why it is not enough? Because the future of content is ultra high definition television. So ultra high definition television, what is it? What does it mean? Because it means a lot of things. UHD TV. First of all, some people associate UHD TV with 4K. Well, partially it's true. 4K, it means, well, more or less 4,000 pixels horizontally. If it is cinema, it is 4096. If it is television, it is 3940. And 2,100 horizontally. This is 4K. 8K, and why I am talking about 8K? Because for Japanese, in Japan, the real ultra-high definition television, their goal, and they are already working on that for the Olympics in 2020, is 8K. Japan is thinking of 8K for 2020. And they started already some experiments via satellite and fiber, looking at delivering that in 2 years, which is double the resolution of 4K. But these are just number of pixels per image. But there are another enhancements which are at least as important as the number of pixels in your screen. It is what in Europe is called better pixels. Not more pixels, but better pixels. What are better pixels? There are different techniques. First of all, the bit depth. Then, the white color gamut, the high frame rate, and the high dynamic range. These 4 aspects can be considered relevant enhancement for your image that could offer a quality of experience for the viewer, at least at the same level of satisfaction as increasing the number of pixels. And I will explain now. So bit depth. What is bit depth? It's simply increasing the number of bits that you are going to use per sample of video component. And here the discussion is if you might know that now we work with 8 bits per sample in distribution and in broadcasting, not in a studio, but just in distribution. The question is that if we will rise to 10 bits per sample or to 12 bits per sample. And the effect, it has effects, many effects, this change. One of them, I'm not sure if we are going to see it in this projector. No. Yes, when you see on TV the sunset, there's an image and you see the sunset. And there's a degradation of yellow from the sun to the horizon. With 8 bits per second, you see discrete steps. You see some bands. This effect disappears if you increase the bit depth. And I had on the left one with 8 bits and on the right one with 10 bits. White color gamut. The second better pixel enhancement. The range of different colors that can be represented by the video creation, edition, distribution, broadcast system will be increased. And here there's an image, probably you are familiar to that, that explains conceptually this enhancement. Look, this curve represents the possible different colors that the human eye or the human system can differentiate, right? And in fact, it's a projection. It has this strange shape because it's a three-dimensional projection of, it's a three-dimensional function which is projected on 2D. Look at this small triangle here. This one is the old or current 709 recommendation from ITU. What does this triangle mean? It means that currently HD TV can only represent these colors. Only the colors inside this triangle can be delivered by the system. With ultra-high definition television, if it has a white color gamut enhancement, look at this bigger triangle here. You will be able to represent a much wider range, especially green tones. So nature images will look, or in fact, they look really differently if you compare HD or ultra high definition television with wide color gamuts. And this part, and I will make a comment later, this part is very good, or easy, I would say. Why? Because it is standardized by ITU. These are ITU recommendations, 709 and 2020. So not a big problem. High frame rate, the number of images captured, delivered by seconds, per second, sorry. And here, again, you have an example, an image by BBC R&D. You see here, this part is with higher frame rate, the number of pictures that you are showing the viewer per second. Probably this one is 120p, so 120 images, frames per second. And this one is current 50p or 60p. And you see here, you do not have a clear view of the image, especially if it is movement, if it is sports. Sports, this is one of the key aspects to have impressive images when you are broadcasting sports, football or whatever. And finally, you have the high dynamic range, HDR. What is HDR? HDR, in simple words, is the difference between the blackest black in your image and the whitest white in your image. So the range of luminance intensity that your display is able to show you. And this is one of the really big technical issues for broadcasting. Well, I would say to any audiovisual system. Why? Because the human eye is extraordinary. It has an adaptive system that enables you to watch every detail in this room independently of the luminance of the specific area. And this is a challenge for cameras and for displays. Here, again, there's an example, but well, it's not bad that we see it a little bit dark, because this is how it looks with current dynamic range, and this is how it looks with high dynamic range provided by Dolby. So really, here, this is another part where it makes really a difference in the image quality. But not only for detail, not only because you see a wide range of luminance values, because it also helps with color. Again, you cannot appreciate it very much, but the original image gives you a wide range of different intensities of this orange-like color, and provides you a really good quality in your perception. So, with all these techniques, how is the standardization roadmap in Europe? In Europe, we have decided to two phases. In fact, they don't call them phases, they call them two different standards. UHD-TV1, which is 4K, and UHD-TV2, which is 8K. 8K started, the work didn't start yet in Europe, so has not been considered yet. But inside 1K, inside UHD-TV1, they have decided on phase one. What is phase one? It is what we have now in the stores. If you go to a store and you buy a television and they say, this TV set is ultra high definition compatible. It is a 4K. No white color gamut, no HDR, maybe some artificial increase on the frame rate, but simply by repetition. It's not that they present you 120p different frames for your quality. They can repeat some frames, so they have a 120 Hz presentation rate. So phase one is what we are currently now, but DVB has already standardized, or is, I'm not sure if it is finished yet, but is standardizing phase two. What is phase two? It is 4K plus the rest of the coloring, sorry, not color, the rest of the techniques: bit depth, white color gamut, high frame rate, and HDR. Okay, very good. So we have some tools to give impressive images to the audience, but the implication, what is the implication? Look at these numbers. The bitrate increase that you require for 4K is 300% the bitrate that you have today. And look, do you see here HDR, white color gamut, and the bit depth? These techniques that provide really good quality of experience are almost for free in terms of bitrate. It's not for free for equipment manufacturers because it has complex implications on cameras, complex implications on the production process in the studio, and complex implications for the screen manufacturers. But really, in bit rates, not really a big change. Very small increase. So, what would happen if we add these techniques to HD? Let's forget about 4K. What if we put HDR and white color gamut on this simply high definition resolution? Look, this is MPEG-4, advanced video coding, and this is H.265, high efficiency video coding. These are already state-of-the-art coding. Look, you can deliver a really, really good quality of experience to the user with, today, this was 1.5 years ago, probably today, 10 megabits per second. With 10 megabits per second, you can provide an extraordinary good image to the user without going to 4K, right? You know already that the resolution has an impact on the distance that you have to watch, or on the good distance, ideal distance to watch your screen. So 4K is useful if you have a big screen and you want to sit very close to the screen, because otherwise you do not notice the 4K effect. There's a law, we can find it, talk about that later. There's a law about the minimum distance that you require, or the ideal distance you require to watch and to appreciate the difference between 4K and HD. But with these techniques, the 10 bits, the HDR, the white color gamut, the number of frames per second, you really, no matter the distance of the image, you really notice the difference. And the implications on bit rates is not so huge. Now, if you combine those techniques, with 4K, I will take the best case, I would say, the highest quality with all these techniques included. You see, these are numbers for advanced video coding, again, MPEG-2, MPEG-4, and this is H.265. Here, you require 27, 28 megabits per second. So in practice, you would occupy the full Dvb-T Two signal to deliver just maybe one program, or maybe one program of ultra high definition television and 2 or 3 small 2 megabits per second standard quality programs. So if, for example, you combine, you go from 120 to current 60 rate, these numbers are from America, but here in Europe we would use 50, you have 20. Then you could have one ultra high definition television content and then another 4 or 5 standard definition programs, or maybe one ultra high definition and then maybe 2 HD, high definition programs. Not, for sure, not 20 programs as you have, for example, here in Russia, or the 50, the 30, sorry, we have in Spain. And these are, these are data from Cable Labs. These are data from IRT in Munich, data from IBU, and they really do not show very big differences. EBU considers the upper bound for ultra high definition television around 22 megabits per second, and with statistical multiplexing 20 megabits per second, well, with high efficiency video coding. There are other coders, and I summarize here because IP networks do not all use MPEG-4 or H.265. These are the family of Google coders, the VP8, the VP9, but really they do not have currently a much better efficiency than H.265. Okay, so we went over content. Now I am going to go on standards. This is the distribution map of standards. Excuse me. There are 4 families of standards distributed around the world. You have ATSC. ATSC is North America, Canada, Mexico, and also South Korea and some other smaller countries. This is ATSC. ISDB-T, this is the Japanese system. The Japanese system, okay, it's obviously in Japan. It is always also Philippines, and most of South America and some Central American countries. The only country in South America, well, there's here Guyana, but the only big country in South America that has adopted DVB standard is Colombia. Currently, it's just an island of a standard in the middle of South America. The rest of South America, inspired by Brazil, adopted ISDB-T. We have, well, in fact, this is another country, is China. China has the TDMB standard in percentage of population of the world, one of the biggest standards. And then you have DVB-T and Dvb-T Two, which is Europe, most of African countries, India, and Australia, New Zealand. But here are some comments. As far as I know, India has not taken the final decision yet. Officially, well, let's put it that way. It looks like there are some decisions that go to Dvb-T Two, but as far as I know, there's not still the final decision to take Dvb-T Two standard and deploy the standard over the country. So, at least I didn't see specific information on that. Also, in Africa, the influence of the Chinese standards is increasing slightly. Well, not slightly, on a big extent. So there are countries especially in the Southern Africa, that are considering standards because they didn't migrate yet to the digital television standard. So they are even considering the Chinese standard DTMB. Looking at the numbers, you see here the combined population in Dvb-T Two, and this includes obviously India. If you combine all any DVB standard, including DVB-S, DVB-C, DVB-S2, well, DVB standards are the most successful ones worldwide. These are the countries around Europe, Central Europe and Southern Europe. Russia is included here in this column. And then you have ATSC, excuse me, which is mainly US, Canada, and Korea, and Mexico. And you have ISDBT, which is Japan and South America. And here, these are the numbers of, these are the numbers of the Chinese standard, the TMB, which is China and 2 small countries around. So I will focus at the next slides on 2 standards, Dvb-T Two, and I will not go into very specific details of the standard. We can have time for that in the question and answer period later, but also on ATSC 3.0, because these are the 2 latest standards. So we come from Dvb-T, and I put this table for comparison purposes. With Dvb-T, we have now this is the common mode in Spain, but it is the same in France and same in Italy and Finland, many other countries. The capacity of the Dvb-T standard is around 20 megabits per second. In the UK, they do not build single frequency networks. You know that all transmitters of the network operating on the same frequency. They just build multiple frequency networks, 1 frequency per area. So they have 24 megabits per second, a combination of 24 megabits per second. And then in Germany, and I included that because in Germany, terrestrial is not the main delivery method, it's cable and satellite. But they have a network of transmitters around the country who is targeting portable reception, not fixed reception. And this is the reason why they configure their system for a lower bit rate, but more robust, to be able to be received indoors. So this enables you to provide 4 to 6, maybe if you squeeze a little bit your compression, maybe a little bit more, 1 more, programs using the MPEG-2 coder. So this was not enough capacity, and this was the reason to develop Dvb-T Two. This capacity is not enough if you want to migrate to high-definition television. Not even ultra-high definition, but high-definition television. This was the driver for the new standard. So the objective of Dvb-T Two was to create a long-term standard for terrestrial, fixed, and portable, which was, the intention was to have it very close to the Shannon capacity limit. And there were some requirements. First of all, use the same infrastructure. So, requirement, at home, you will not need to change your antenna. You will not need to change your installation to your home. Yes, you need to change your television or buy a set-top box. But the receiving infrastructure is the same. Also for transmission, antennas, combiners, waveguides, rigid lines, all this hardware, all the piping in the transmitting side could, in theory, keep constant, keep unchanged. And very important specification, at least increase 30% the capacity of the standard, at least. And then some other features that I would summarize all of them into one word, is flexibility. Why flexibility? Because you saw it in a previous slide. Each country is completely different. If we analyze the market of broadcasting here in Russia, has nothing to do with the market in my country. Economic factors, geographic factors, language factors, many factors. So you need, and Dvb-T is very rigid, has only, well, not only one, but very few feasible configurations. That they have difficulties in adapting the networks for the specific of each country. I will not go into the details of the blocks, but where is the magic of Dvb-T Two? The magic of Dvb-T Two is one of the major factors for magic is these 2 blocks, which is the coding. The coding in Dvb-T Two are the LDPC codes. which were, for those who you do not know, they were invented in 68. In 1968, there was a gentleman. He was called, name I don't remember, Gallagher is the surname. Gallagher. He was a PhD student that developed as a PhD the LDPC codes. And at that time, this is 1968, I can imagine people around him laughing because, okay, you did a great thesis, will never be true because you have invented such a complex maths to do coding that will be never implemented. But you already know, or probably should know, that in technology you cannot never say that. Because maybe it takes 40 years, but in 40 years, the advance of technology will enable that your theory comes into one receiver. And this is what happened. In 2003, it was Dvb-T2, the satellite system. The DVB satellite system introduced for the first time the LDPC codes on a receiver, increasing, and this is where the 30% percentage comes from. It has a 30% better efficiency than other type of codes like FEC, like convolutional plus Reed-Solomon of Dvb-T, for example. So this is where the improve in efficiency, where the major improvement in efficiency comes in Dvb-T Two. And in fact, these two modules, for the sake of simplicity in technology, they were just slightly modified from Dvb-S2. Some other blocks came from Dvb-T because Dvb-T2 is OFDM, you have word interval, the mapping schemes, most of them are the same. Well, there are many commonalities. And there were some new modules to Dvb-T2, which I would highlight. One of the highest one is the frame builder, which is the module that enables you to create PLPs, for example. And what are PLPs? PLPs are physical layer pipes. They enable the allocation of individual level of robustness in your service. In Dvb-T, we saw before the table, in Spain, you have 20 megabits per second. You put a transport stream on that 20 megabits per second, and all the 6 or 7 programs have the same robustness. Even if you are the public operator, I imagine that here the content is similar. In Spain, the public operator, the public broadcaster has the TV1, we call it TV1, which is the news, the big programs, the very good films, they are all on TV1. TV2 is cultural programs, documentaries with low audiences. Also, they have a kids channel with a lot of cartoons, and there's a sports channel, and they have another program, but I cannot remember which one. It is obvious that the impact of quality is not the same if the TV1 fails or the, well, in fact, I think that the critical one will be the kids. If the kids fail, then it's a nightmare for all of us that have small kids. Then the biggest priority should be the kids channel. But you cannot do that, right? Because all the contents have the same robustness. In Dvb-T2, you can differentiate different levels of robustness. So in fact, this is very important also for the network operator, because you can have different coverage footprints on your network. And this has complex market and also planning implications. A feature important, and we will talk about this later, is that in theory, Dvb-T2 is not tied, physically tied to transport stream. Dvb-T, yes, because those for you who make transmitters, the synchronization of your electronics is the MPEG-2 packet, physically, on the physical layer. With T2, this does not happen, but practically, all the networks that I know on Dvb-T2, they all work on MPEG transport stream. they did not go to the other possibilities. And I am not sure if all the equipment on the market is able to work with other streams which are not MPEG transport stream encapsulated. Probably not, I don't know. Because in theory, when we will speak about IP later, in theory, the MPEG 2, oh sorry, MPEG 2, Dvb-T Two is not tied to transport stream. In theory, you can get a generic continuous stream. You could put the IP packets. The problem is the efficiency in the overhead that you have to put into your content. So probably this is why most of them keep tied to transport stream. So the efficiency that I mentioned before, look, here this is a representation of the Shannon curve. This is the limit of capacity that theoretically you can achieve for a given bandwidth and a given signal-to-noise ratio. So look, these are the modes of Dvb-T, and this is Dvb-T 2 modes. So look, really close to Shannon, really, really close to Shannon, less than 1 dB. And this is 2009. And ATSC 3.0, which was approved last year, 7 years after Dvb-T 2, it has better efficiency. But when they say better efficiency, yes, it is better. But how many fractions of a dB better? Because LDPC already gets very close to Shannon. So in this part, there's not any room for improvement. The range of megabits, and this is flexibility. With Dvb-T 2, you can operate almost with a 0 dB signal-to-noise ratio and 7 megabits per second, and you can go up to 50 megabits per second. But look, these are Gaussian channel numbers, because for practical networks, this value would go up to maybe close to 25, and 25 minimum signal-to-noise ratio is close to the limit of practical terrestrial network deployments. The coverage would suffer quite a lot. But look, this is 50 megabits per second. In fact, what is this mode for? What can you use this mode for? For example, for links. You can do video links with Dvb-T 2. You can do camera links with Dvb-T 2 using those configurations. If you have a very directive antenna, you have a good pointing situation between transmitter and receiver, you can use Dvb-T 2 to do video transmissions from point to point. Another feature of Dvb-T 2, you know that Dvb-T had the possibility of doing 8K and 2K, the number of carriers in the spectrum. Dvb-T 2 extends it up to 32K. There are also modes below, but nowadays with very small practical application. The real applications in the future will be 16 and 32K. I do not know which is the mode here in Russia. It is 16 or it is 32K, Dimitri? Do you know it? 32K. Okay, 32K. So this gives you more capacity, but why? Why more capacity? Because it enables you to have better efficiency in the word interval for single frequency networks. So having 32K, it gives you the possibility of having distances between transmitters of up to, well, I don't know by heart the numbers, but probably close to 200 kilometers, theoretically. And this is of, excuse me, this is of fundamental importance in countries like Russia, with huge regions where the population is not very dense, and you can put one big transmitter to cover that big region without interfering other parts of your single frequency network. This is critical for regions, for large countries. And finally, another very interesting feature, which was introduced at the very first specifications of design specifications of Dvb-T Two, and it is the feature extension frames. Why? Because DBB did not want to change the standard after 5 years. So what they did, okay, let's create a mechanism. So in the future, if we find another standard or we find another application that requires that we put a different physical signal on our channel, we will create what we call a feature extension frame. If a feature extension frame comes and you have a Dvb-T Two receiver, the T2 receiver will just stop, let this new service, this new frame pass, and then again synchronize into the next Dvb-T Two frame. So in theory, you can invent a different signal there, put it there, and your receiver will not fail, let's say. Will not access the new one, obviously, but will not fail. If we compare it, the numbers with the numbers we did before, 20 megabits per second, Spain, 24 in UK. One of the proposed modes that will be mostly used will convey 33 megabits per second. And you have the increase, the evolution in the efficiency, in the number of pilots, the synchronization symbol overhead, the new codes here, LDPC and BCH. So, in summary, it is Dvb-T plus 50% better efficiency or 100% better efficiency. It will be depending on the country and the configuration. So ATSC 3.0, the goals were very similar to Dvb-T Two. The history, in Europe we have Dvb-T Two, but in the US they have ATSC 3. Why? Because in the middle, we came Dvb-T, Dvb-T Two. They had ATSC 1. They created in the middle what they called ATSC 2.0, and it was to integrate a portable reception mode and also some interactivity features that I do not know the details about these interactivity features. But in fact, this ATSC 2.0 was a commercial disaster. It was not implemented, deployed. At least that I know in the US. In Korea, I don't know, but in the US, it was not deployed. 2.0. So that's why from 1.0 they went to 3.0, because they had these small modifications in 2004 and 5, I think. So, what is the difference with Dvb-T Two? There are many similarities. It uses OFDM, it uses LDPC coding, different codes, but LDPC, not compatible, but LDPC, and it uses, they don't call it physical layer pipes, but they are physical layer pipes. I don't remember the name for that in the ATSC 3.0, but they have physical layer pipes. You can assign different robustness levels to different services. But also it has significant differences. The biggest one, this is an IP-centric standard. It's on the protocol stack, it is IP. It's very similar to broadband protocol stack. We will see it now. And also it has some physical layer technologies. It has non-uniform constellations. It has a technology which is called layer division multiplexing, which is a type of NOMA, non-orthogonal multiple access. It has a synchronization based on a signal that they call bootstrap, which is compatible with LTE. It's 5 megahertz wide. And they have channel bonding, but this is optional and very unlikely to be implemented. So if we look at the protocols, look, this is the protocol stack of Dvb-T Two. Look here, is based on MPEG-2. And everything from the TV application to the codec, they all fill into these MPEG-2 transport stream packets. If we look at the model of ATSC 3.0, and I will not give you the details, what I want you to realize here is that, look at this column here. This is IP broadband. This column here, this is the broadcast. Up to this layer, you see they go in parallel because they are both IP. You could route one service here to the broadcast, and this is the intention of the broadcaster here, you could have your programs into the broadband delivery method without major complications. You can do that also in Dvb-T Two, but not so efficiently. You lose overhead because you have to encapsulate packets into MPEG-2, and this is not efficient at all. And well, there is a complex process there. And another important feature here, you see these two blocks. The standard already takes into consideration that there will be linear services, so live TV, and this is what this protocol does. Enable the delivery of linear television, the traditional programs, but also with this one, with root, the standard can deliver non-linear content. So you can push contents to your receiver because most receivers already have a hard disk today. You can put content on your device. You do not know, but the broadcaster is putting contents on your box. And maybe this afternoon, one of the commercials arises. The commercial was in a hard disk, was not sent alive. But somehow they know that you will like this commercial and it will pop up. Potential application. The structure of the ATSC 3.0 signaling time is first a bootstrap, and then this is the framing, which is not exactly the same as Dvb-T Two, but could be associated in parallel to that. But what I wanted to highlight here is this signal, is the bootstrap. This is the mechanism that ATSC 3.0 uses for future extensions of the standard, the equivalent to feature extension frames in Dvb-T Two. So it's a signal which, in fact, is not included on the television standard. They have created a separate standard. So the bootstrap signal is a standard, and then they have the television standard. Why? Because if there will be a, imagine, ATSC 4.0, the bootstrap signal can be maintained untouchable. Or if you want to deliver a new service, you eliminate, imagine that broadcasting disappears. Again, stop the recording. Terrestrial broadcasting disappears. And the size of the channels of the UHF band is changed to accommodate cellular signals. Look, the frequency width of this signal is mysteriously the same as the cellular channel bandwidth, 5 megahertz. Right? So this is another unique aspect of ATSC 3.0. The bandwidth of the rest of the frames is the standard bandwidth for 6 megahertz, because in the US and in Korea, the bandwidth of the TV channel is 6 megahertz. Here in Europe, we have 8 megahertz. So, don't be scared. I will not explain every module. Look, this is an overview of the physical layer. The upper part, what is the upper part? The upper part is an interactivity channel. Why? Because China wanted, well, Chinese partners participating to the standardization process wanted to design a return channel specific to television. From your home, your antenna will be transmitting interactivity without the cellular or broadband connection. This is a dedicated physical signal to connect you with the broadcaster. I don't know in China. In the US and in Korea will never be implemented, well, rolled out. So this is, well, that, look at the uplink from your television. Then, this module here, what is that? It is the equivalent, for those of you who are familiar to Dvb-T Two, is the T2MI interface. This is the baseband frames packetized and encapsulated into a frame, and you send these baseband frames to the transmitters. Okay, so this is what they call Fish Studio, but it is baseband frame. And what is that? This is the equivalent scheme of what I showed before about Dvb-T Two, right? So you will find a lot of very similar modules, except for this one, the layer division multiplexing, and this one, the bootstrap, which is a specific signal of the ATSC 3.0. The rest of modules, they are not compatible, obviously, with Dvb-T Two, but basically they have the same technical or physical principles. They are time interlevers, frequency interlevers, bit interlevers. They have the PLPs, they have the PIPR reduction, there's also a MISO configuration, the FFT, the word interval, the pilots, basically the same principles. Some numbers, again, well, I will not go into detail. If you are interested in the questions, I can answer that. Another difference relevant in ATSC 3.0. In the modulation, the mapping of the constellations is non-uniform constellations. You see, we are used in Europe to squared constellations, QAM, QPSK, etc. All the constellations in ATSC, they are non-uniform. This means that the distance between stars of the constellations are not constant to improve capacity, right? The gain that you have with these constellations, less than 1 dB. In terms of Shannon limit, they are better, but really, let's say, maximum 1 dB. Again, this is a nightmare for manufacturers. It's a nightmare for manufacturers because the LLR computations, for those of you who are familiar with signal processing at the receiver, the computations of the LLRs and the probabilities at your receiver become much, much more complex. Another technology, layer division multiplexing. What is layer division multiplexing? It means that you are transmitting on the same channel 2 signals, one on top of the other. So you can, for example, send one service for mobile receivers and one service for fixed receivers. The service for mobile receivers is a very low bit rate, but very robust. And the service for fixed receivers is very high and requires high signal-to-noise ratio. And you send both of them at the same time. So what does the receiver do? It gets the whole ensemble, the 2 signals, decodes the upper layer, cancels it, eliminates it, subtracts it from the ensemble, and then decodes the second component. So if you are in a situation where both components are received with high signal-to-noise ratio, your receiver gets the two services. If you are very far, you will never be able to access the lower one. But the upper one, because it is very robust, you always get that. Because the upper one is prepared to be received around 0 dB or minus 1 dB. So very strong. And this is part of the standard already. This is an outline of the LDM, which is combining the two components before modulating and then doing a more or less complex cancellation. And I'm showing that because we participated into the development of this LDM. It was a development done by ETRI in Korea, by CRC in Canada, and by our university in Spain. A few comments about spectrum. Look, this is the spectrum for broadcasting in 2006. From 470 megahertz up to 862. In 2007, it was decided that the upper band was given to broadcast. To broadband, to mobile communications. And in fact, it was said that it would be shared between broadcast and cellular. This was recommended by some EC consultants. At that time, it was expected the most realistic scenario for free-to-air services, and it was expected that this transition would start in 2015. But what happened? In 2012, there was a World Radio Conference, and driven by the North African countries, the 700 band was also given to cellular, to mobile communications. At that time, they said, and this is for the very first time in ITU history, they say, this is going to be co-primary. For those of you who are not familiar in allocations, primary service is the one that has to be respected. If you use one frequency and you are a primary use of this spectrum, if someone is disturbing you with an interference, the government says to those ones, no, shut down your station because you are not primary. The primary is cellular or broadcasting or whatever the service, satellite. So primary. And at that time they said, no, these two services, broadcast and cellular, will be co-primary. So at the same time they have the same, but this is unpractical, completely unpractical. Why? Because the shape of the networks is completely different. In cellular, you have one station every 100 meters in big cities. So it will be interfering the broadcast service for sure. In other situations, you have a 100 kilowatt television transmitter tower in the middle of the city that will be interfering all the cellular network in that area. So co-primary, what means co-primary there? It's purely theoretical. So this was abandoned. And okay, and it was the expectation that this is the final situation. But what happened is that the ITU in 2015 said, okay, we will not change the allocation in this band in the next World Radio Conference that is going to be next year in Geneva. But in 2023, and this is important for the cellular related comments later, there will be a full review of the spectrum of the UHF band in 5 years from now. And this could be the time where ITU decides no more broadcast band ever. All these band are allocated to cellular communications. And it is already official that this topic will be one of the agenda items of the 2023 World Radio Conference. But at the European level, last year there was a decision of the European Parliament stating that the sub 700 band, so all the frequencies below 700 megahertz, will be maintained in the European area, in the European community area, until 2030. So the European Commission has secured all those frequencies to broadcasters, well, to broadcasting service until 2030. But in the regulation, look at what they say. While taking into account the principle of technological neutrality. What does it mean? What happens if 3GPP, the cellular people, come with a broadcast standard and they say, okay, we will take these services. And we will include these services as part of our offer to our customers. And we will include a free-to-air mode that enables you to receive this service into your television without a SIM card. So the future is open in the next 10 years. These are the coding performance expectations for the next 5 years. We are now here. This is HVC coding. The reference of the coder is 2016. So it is expected that the next coding generation, which is the GVET, the GVET is already planned. It will be standardized after 2020, and the first implementations expect to have the required bit rate as we require today. So remember the numbers I gave before. If we require today 28 megabit per second for ultra high definition television, we might need just 12, 14 megabits per second for ultra high definition content, right? And even more, there's what they call boosted HEVC and boosted JVET, which means we will not change the standard. We will change the standard, but basically it's the same structure for coding. But we can do some small, or let's say not so small, adjustments on the standard and reduce it even more than half of the bit rates. Yes, and these are data, it's not my invention. These data are from Harmonic. You know, the Harmonic company is one of the bigger players on the video compression equipment, and they already have plans based on these techniques. It's elastic coding, which means playing with the hardware, doing parallel processing what is necessary of your receiver. Machine learning, very important. They are studying how to apply artificial intelligence to your coder. So the application of each one of the techniques will be applied intelligently by your receiving. And then one very important feature. In audio, we already use that. You know the spectrum, the spectral curve of your hearer that is used by MPEG-3, by MP3, and all the audio coders use this psychoacoustic model on the coder. This is not used for video coding. But they have already started investigating in how to apply, why should we code things that we cannot watch, we cannot see? And focus on the content that it is relevant to your eye. They are already exploring that. And this is what they call boosted HEVC. And then, my final slide. We are approaching a limit, the Moore's law, the implementation of chips is getting to the limit. You remember the Moore's law? It means I will double with no significant increase in price. Every 2 years, the number of transistors that I can integrate into the silicon. Okay, it's already 4 years that we do not anymore feel the Moore's law, right? And if we look at the width of the transistor into the silicon, we are now on the generation of 14 nanometers, 15, 14 nanometers of the width of the transistor inside the silicon. They are already, well, we already know that when we arrive to 7 nanometers, which is already experimental, and there's a prediction for 5 nanometers, the current technology will not work, because then quantum subatomic effects arise into the chips. So we already are very close to the limit of what we can do with current technologies, and this is very important. Some people are very negative about this number, because oh, this is the end of technology as we understand it today, because we will not be able to continue improving our systems. I disagree completely. Look at Gallagher. It's probably, someone was telling that to Gallagher at that time. The thing is that, and this is why I put this image, this is cost versus years in developing integration in chips. The cost has become exponential for very small increases in efficiency. So what we need to do, we need to find a different scope of technologies. I don't know, graphene or nanotechnology in chips, I don't know. But silicon MOSFET integration has reached, as a technology, the limit. It's like steam machines. Steam machines have a limit. It's not that you cannot go any further, but you need to change technology. So this is happening also with electronics in the close future. Okay, so I will stop here. And now we can discuss and